Alright, so last lesson we are here and let me set that properly. Okay. We established that an object that is rolling has translational equilibrium and also rotational velocity considering from center. So adding up the two velocities, we can actually get this kind of velocities. Okay. Get this. So if you say that something that's rolling, right? Rolling motion with the center of mass moving at v, right? It's actually the sum of the translational speed v, something flying around, and due to the rotation of omega. Okay. One more time, gives you this. Okay. Can? Right, so in this context, right, it's very easy to, because here the v is 0, it's very nice to use this as one of the points of reference. Okay, we'll see this. So since p is at velocity 0, p is at velocity 0, right, we can consider the kinetic energy about point p, and it will be this equation. Okay. The moment of inertia about point p and the omega square about p. They will all be rotating the same omega because they belong to the same solid object. Now, we know that the moment of inertia of p by parallel axis theorem, you already still remember what parallel axis theorem, if not, please figure that out, is that the moment of inertia about p is just the moment of inertia about cm, about the center of mass, I about the center of mass, plus the mass of the object times r squared, where r is the distance between the point or center of mass and p. Okay? Following? So this, then if you do some mathematical thing, the kinetic energy is just this thing, right? You sub in IP equals to ICM plus IMR squared. Get this? The first part you don't change. The second one, R squared omega squared is just CM squared. So what do you tell? What do you see? The total kinetic energy of this body is the translational velocity, half mv squared, right? The object is moving with speed v, right? Half mv squared. Plus this rotational kinetic energy, half moment of inertia omega squared. 一加 right? Right, which is the words that I have under that. Okay? I've notes you don't have.
Oh,
It's the same as,
last one.
yes.
Okay, thank you.
So example, right, a ball that 6 cm rolls without slipping over a horizontal plane with velocity of 4.0 revolutions per second. The mass of the ball is 0.25 kg. Find the kinetic energy of the ball. So the total kinetic energy as per the previous equation is half mv squared, the translational kinetic energy, plus the rotation energy. Then I ask you to remember the moment of inertia of a sphere, right? Moment of inertia of a sphere is 2 over 5 m r squared. That's why we have this. Sub that in, we get this r squared omega squared is just v squared. So put all together is 7 over 10 m r squared omega squared. Do we know the v? We don't know the v, but we know the omega, right? Oops. So sub that in, we get the answer of 0.10 joules. Okay? So now you actually have a bit of a piece of information that's more than your peers, right? At this point, if I show you a ball that is sliding, if you know go bowling, right? Sometimes the ball slides and then rolling, and the ball that's rolling with the same speed, which one has more kinetic energy? The one that is rolling, right? So in the event that just in case you have a sliding rock coming towards you and a rolling rock coming towards you, and you have to be hit by one of them, choose the one that's sliding, just in case. Just in case you're in that kind of situation. Hopefully not. Okay, anyway. Yeah. Next, given two vectors A and B, the vector product is another vector C. You will learn this in J2 mathematics, which is unfortunately too late because your Olympiad is in J1. Right, so learn it now. Cross vector A. So A is the one that is further higher up. A cross B. So let's say A is here, B is here. A cross B, C vector points up. Okay, C vector points up. So magnitude of C is AB sine theta. That means I want to find the perpendicular AB sine theta. That means the perpendicular distance of A to B, or the perpendicular distance of A to B or B to A. Right? That means either I resolve B to be perpendicular to A, or I resolve A perpendicular to B, and I multiply the two together. Okay? So this is the mathematical thing. This one, just remember. It's the area formed by a parallelogram. Okay, not a problem. Okay, so C must be perpendicular to both A and B vectors. Okay, so this is something that we have to introduce to you, the mathematics. Next is a cross product. In last lesson, we introduced top, right, as R cross F, as R times F, force times perpendicular distance. But in your H2, right, and in your O levels, you always learn force times distance, force times distance. It's not true, you know. I mean, it's true, but it's not complete, right? So you always know moments to be force times distance, right? Let's say I have a plank here. I apply a force down. I apply a force up. I rotate it this way. What is the moment? You will just take the moment as a value, as a number, right? But actually, moment is a vector, right? So you need to cross it. So you need to force R cross distance. So the radius is, let's say this is the point. R is this way, force is this way. So I cross, so the moment points towards me. Okay. Right. Same thing. So top is R cross F. So if you look at this, this that's spinning, right? Take R, which is the position vector, cross the F. So R is this way, cross F, which is point up. Sorry, right hand. R cross F. Okay. Okay, moving on. Angular momentum, same thing. Angular momentum now we introduced to you, right? Momentum you have learned in dynamics. Yes, some of you will have had that lecture of momentum. Momentum is mass times velocity, product of mass and velocity. Angular momentum is R cross P. Okay, R cross P. So it is like momentum, but you include the radius from the point of observation. Okay, from the point of observation. So R cross P. So now what do we have? Torque and angular momentum. This is just going to be a lot of derivation, but the important part is the answer. Okay. Force using your Newton's second law is the rate of change of momentum. Okay. Next, angular momentum, the differential angular momentum. If you take angular momentum out, we know that angular momentum is R cross P. Then by the differentiation rules, if R is a constant, then we dp dt. If P is a constant, you add T, add together, you get this. But because dr dt is V, right? R is a position vector. The change of a position vector is just the velocity. Okay. V cross with V is nothing because it's in the same direction. V cross with the momentum, which is in the same direction, is 0 because there's no angle between it. Right? If you draw a parallelogram, the area is 0. right? So one part of it disappears. So this part disappears. Which means that the angular momentum, the rate of change of angular momentum is just r cross dp dt. But we already know what r cross dp dt is your torque, which means that torque leads to a change in angular momentum. We do all this to show that if you apply a force perpendicular to the object, it turns. Which, cool, huh? You will say, wow, I do this. I already know it when I was young, right? If I apply a force on this spins, it's not an issue. But we are now able to quantify it. How much force you apply spins it by how much, right? Recently, you have also learned about SpaceX. They launched a shuttle. Elon Musk, the handsome and intelligent guy. Okay, the intelligent guy, minus the first part, right? He's a very techno guy, and he formed a company to launch a space shuttle up, to use the shuttle, which is an amazing thing, right? And in many of space travel, right, if you also recently watched Martian, have you watched The Martian, the movie? Right, Martian, the movie, yeah. Strange story. Oh, this is going to be recorded, but never mind. I was on my honeymoon with my wife, but that was okay. No, only the parts that's relevant. Then I found this book that was interesting, which is The Martian, right? I couldn't stop reading it. But anyway, the book has more science to it. It's amazing. If you are interested, you should go read the book instead of watch the movie. But on the movie, there's one part where when launching, I think something liquidified, or was it another rocket anyway? So when you launch a rocket, right, if it liquidifies and it starts spinning, right, the angular momentum will take away some of the energy, which is why his height was not enough to reach the surface, something like that. Okay. So yes, so the point is, now that we know about this, right, and a lot of rocket sciences, when you launch something, spinning becomes a very big problem, right? You want to be able to counter for it. You need to have some energy remaining to counter the spin. Okay? So it's not negligible. But unfortunately, your H2 friends will not know this. Feel too bad for them. So sad. Anyway, right, it's like learning about left hand but not knowing that there's a right hand. Right? Because these two things are so important in any classical physics, right? Momentum and angular momentum are key fundamentals. If you go to a physics professor in university, like let's say in US, and you tell them, in my H2, I have not learned angular momentum, he'll look at you and he will fall over his chair, I think. Unfortunately, we are limited by time. So if you are interested in physics, you should learn about this, okay? Anyway, so torque is the rate of change of angular momentum. There you go. And if we differentiate with respect to time, right, we know that angular momentum becomes this. You differentiate with time, you get this, which is just, in fact, just moment of inertia times angular acceleration, which is what you have approved a long time ago, because you have seen in very many pages ago that torque is equals to moment of inertia times angular acceleration. You already learned that. Okay. So the sum of all the torque, not the sum of text. Okay, please don't read this wrongly. It's not sum of text, it's the sum of all of the external torque gives you the LCDT, which is IO alpha. I alpha, okay? Right, let's look at this. And like physics in the dynamics, right, you learn about conservation of momentum, linear momentum. There is also an equivalence with the conservation of angular momentum. Okay, so if the sum of external torque is 0, there will be no change in the momentum. Okay, which means that the momentum will be constant. Right? So for rotation about fixed axis, right, the moment of inertia times angular velocity initially will become that at the end. Okay? Is it too slow? Okay. Must catch everything I'm saying now must catch because this will be your bread and butter for your Olympiad. The first 3 sessions, most of the things you will know in H2, so really not too worry. So last week's one, this one you must know because your H2 will never cover. And also, your friends who are excused, right, will ask me to give excuse. I do look at the video count and see how many already sees the video. It's at 1. And I know which one. Because one of the video I put private, only one person asked me, why Mr. Ho, this is private? So thank you very much to that student. You know who you are. I appreciate that. The rest of you, okay, anyway. Oh, that was recorded. Yes, those of you at home who have not watched this video. Okay, anyway. A star rotates with a certain amount of days, right? So it explodes and collapses into a neutron star. So you have something that's wide and big and collapsing into a neutron star, right? Can you imagine? You pack 10 to the power 4 kilometers of mass into 3 kilometers radius of mass. That's extreme packing, right? That's extreme, huh? Right? But that's your neutron star. Super dense and super heavy. Right? But what is the period of rotation? So let's start. This star rotates with 30 days. Makes sense, right? Anything rotates about its axis in 30 days. The Earth rotates about its axis in... Did anyone say 30? No, the Earth rotates about its axis in 24 hours. What rotates around the Earth in 30 days? The moon, thereabouts. Okay, so this star's rotation is like the moon's rotation, right? Rotating by its own axis. There are some assumptions. Because it's an explosion, naturally you should expect some mass to be lost. Boom, some parts goes away, but you must make some assumptions. So these are the assumptions. Mass is the same, no external torque, sphere with uniform density before and after explosion. Because if it's not uniform, you know the moment of inertia will be different, right? If it's more dense in the center and more light at the side, the turning speed will be faster. If it's more dense at the side than at the center, the turning speed will be slower, right? You all hear what I'm trying to say? Yes. Right, so you have this. Conservation of kinetic energy, conservation of linear momentum. Oh wait, is there answers? No answers. Let's try. How would you do it? No answers. But it's something like this. Okay, so let's copy and paste some things. We'll see. Okay. Oops. This one must hold true. Correct? Oh, this is something different. I should change this. Oh, I can't. Okay, so first, we must establish that the momentum stays the same. Conservation of angular momentum. And we have this. So maybe I can cut this. Okay, I can. This. What is the rotation, angular moment of inertia of a sphere? It is 2/5 m r squared, right? So that's not a problem. We easily write that down. 2/5 m r squared equals to 2/5 m r squared. Okay. This is the initial. This is the final. You realize that 2/5 cancels away, m cancels away. Correct? Then all you have to do is to substitute in the values for r and the initial angular velocity. Right? Can? So omega is 2 pi over t. Your t must convert 30 days to a seconds. Then you should define this easily. So this is not a problem. R squared is not a problem. this can be found like this, you can find this. Okay, I'm not going to give you the answer, but it should be something that's pretty fast. Okay, so once you get this, just compare with your friends. You should all get the same answers. Moving on. So when you're given a question, right, there are a few conservation laws. Conservation of energy, right, kinetic and potential, conservation of linear momentum, and conservation of angular momentum. So any isolated system. Next question, you have a disc that's spinning, and you drop a wax on the side, right? So now the side at 8 cm away from the center, the mass is increased, the moment, angular momentum is conserved, right? So initial angular momentum will be this, final momentum will be the initial moment of inertia of the disc plus the moment of inertia due to the added wax times the new angular velocity. Okay, and these two momentums must be the same. Okay, we are assuming, of course, that the wax has no angular momentum at the start. So once you have this, these two angular momentums are the same. This equals to this. Sub in everything, you get 32. Okay, not that difficult. Any questions at this point? Oh, okay. All right. Right. So this is once again the comparison between linear kinematics and rotational kinematics. Okay. Good to look at this chart once in a while to refresh your understanding. Last example, if I'm not wrong, a heavy flywheel of 15 kg, assumption is the mass is uniformly distributed. Of radius 20 cm is mounted on the horizontal axle of 1 cm. Negligible mass compared to the flywheel, so the axle has no mass. But if the axle has mass, can you do it? Oh, yeah. Right. We assume that if the axle is thin enough, then we can neglect the moment of inertia because it's spinning about its own axis. But if it's not thin, then you have to factor that in. Right? But for this case, we assume that the axle is light enough that we can neglect its mass compared to the flywheel. So, while this thing is actually quite heavy, 20 cm with 15 kg, so the horizontal radius of 1 cm, okay. So it's a hollow cylinder, yeah? Hollow cylinder, right? So neglecting, or a hollow disc, neglecting friction, find 1, the angular acceleration is the force of 40 Newton is applied. So if the force of 40 Newton is applied tangentially to the radius, right? Tangentially to the axle, that means at the edge of the flywheel, right? You get a torque. Okay, but here I worked and showed you the moment of inertia first of the flywheel, so half mr squared. But here I think the assumption is not exactly right. Right? If you want to be very critical, this is not the correct working, right? Because it's mounted on the axle. You should take half m bracket r1 square plus r2 square, right? There, sure. Do we have that? Where is it? This one, right? No. So I think the answer here is incomplete. Please change it. Okay. Because the axle is of 1 cm, the moment of inertia is not correct. Okay. The moment of inertia is not correct. Next, you apply a torque. We have a force times the radius. This gives you a moment of inertia times the alpha. Angular acceleration. It's essentially just rearranging some of this. So this value 0.30 is wrong. It should be bigger. And hence you should have a smaller alpha. Once you have that, they ask you what's the new angular velocity. So new angular velocity is the old angular velocity, which is 0. Right, times the angular acceleration times time. So you change this, you should get a smaller angular acceleration, you should get a smaller final velocity. Right, so here, a surprising 1 cm axis will affect us. Because it's a disk with a hollow center of 1 cm radius. Okay? I will have to change the notes. Sorry about that. But now you all know, okay? Done.